Okay, so welcome to 2024 for our first video. What we have is that we want to evaluate this nice little form find the value of our following infinite series that utilizes the Riemann-Zeta function. So we have the infinite sum at n is equal to 1 to infinity of n divided by 2 to the power n multiplied by the Riemann-Zeta evaluated for n plus 1. So some things going on here is that what we want to do for this is that there's a little result that we actually want to prove first before we actually get to actually proving the actual result that we want to achieve for. So we'll be using that, and then also within that utilization there's going to be some formulas involving the digamma function specifically. Of course, that and another constant we'll be using actually is the Euler-Mascheroni constant involved with that as well. And then the nice value actually comes down to a simple trigonometric answer, which you will find out eventually if you decide to skip to all the way to the end of the video or not. That's up to you. So with that out of the way, why don't we actually just jump right in? So for our result, we want to prove the following infinite sum. So we have the infinite sum at n is equal to 1 of x to the power n, and then multiplied by the Riemann-Zeta of n plus 1. We want to show that that value is going to equal to negative lowercase gamma and then minus the digamma function evaluated at 1 minus x. This being, of course, that we want that the absolute value of x is strictly less than 1. So to prove this, we're actually going to be utilizing the following definitions for both the Riemann-Zeta function. So you'll see that what we have is actually in the form of a double sum. So we have the infinite sum, n is equal to 1 of x to the power n, and of course that's multiplied by the infinite sum at m is equal to 1 for, let's say. So what this achieves is that this is the same thing as written as 1 divided by m to the power n plus 1. Okay, so what I can do is we can actually interchange our sums over here because both of these are both absolutely convergent, so it actually validates this. So now I have the infinite sum at m is equal to 1, so m is going to be our first index we're dealing with, so 1 divided by m, and then multiplied by the infinite sum at n is equal to 1, and then we have that because thankfully we can interchange this. This makes things a little bit easier, so we have that this is x to the power m divided by, or at n to the power n, and what I can do is, of course, we can use, as you see here, this is actually in the form of a geometric series such that it's within that common ratio for, or rather with our absolute value of x divided by, is strictly less than 1, so that helps. So that means I have the infinite sum at m is equal to 1 divided by m, and then all this being multiplied, so I have x divided by m and then divided by 1 minus x divided by m. Then simplify some things further, so I have the infinite sum at m is equal to 1 of, now this is going to be, so 1 divided by m, and then simplify that, so I have x divided by m minus x. Okay, so to continue further, so what I can do is we can actually break this up. Well, also at the same time, you can also use this in the form of like a partial fraction decomposition, or in other words, you could use this in the form of adding and subtracting a zero term, whichever way you want to use it. So what this does is that, and also at the same time, it's like kind of like breaking out that sort of linearity we'll be using, kind of, well, not exactly. So the infinite sum at m is equal to 1. So this is, in other words, this is the same thing written as m and then subtract m minus x, and then divided by m multiplied by m minus x, and then this can be written as, so the infinite sum at m is equal to 1 over here, so we have 1 divided by m minus x, and then subtract 1 divided by m. This is what we have so far. So now there's something we want to write down and note, and that's specifically in the case for the digamma function. So it has a nice little series representation, so I'm going to write this for the note, that the digamma specifically at 1 plus z is going to equal to the negative Euler-Mascheroni constant, and then add this with the infinite sum at n is equal to 1, we'll just say n for this, for example, of 1 divided by n, and then subtract 1 divided by n plus z, such that for z does not equal -1, -2, -3, and then so on and so forth. So that means the negative integers it does not take into account for. And so if I replace z, so let's replace the different input for negative z. So that means the negative, so I have the digamma at 1 subtract z. So in other words, that's the same thing. So it's going to be negative Euler-Mascheroni constant of plus the infinite sum at n is equal to 1 of now 1 divided by n, and then add this, or rather subtract 1 divided by then n subtract z. So what this entails is that going to over here, so now let me actually continue forward over here that, so let's see, the infinite sum at m is equal to 1 of 1 divided by m minus x subtract 1 divided by m. So now putting that back, so now that's the same thing written as, so minus, and I'm going to put the parentheses of the digamma at 1 minus x, and then add this with the Euler-Mascheroni constant lowercase gamma, and if I just distribute the negative symbol, so that means I have negative lowercase gamma, and then subtract the digamma of 1 minus x, which of course is exactly the result that we have over here. So this actually proves our little result over here. Okay, so that's out of the way. So where do we go from here? So why don't I actually take our little result over here, our what is it? So we actually take our result from over here, and let's actually differentiate it in respect to x. So now let me write out our little objective here. Now, if I differentiate with respect to x of this little result over here, so what we have is that we just utilize the, the power rule. So the infinite sum at, now what is it? N is equal to 1. Now this is going to be, so n and then times x to the power n minus 1. So this is still the lowercase, or the Riemann-Zeta at n plus 1. And then take this derivative over here in respect to x, so let's just utilize the chain rule. So it's a subtract from the minus x, so that means that becomes a positive. So the derivative at the digamma of 1 subtract x, okay? And so now let's actually plug x. Let's plug x equals 1/2. And so what this yields us, so let's see, and then I'm also going to take things another step further. So n is equal to 1. So now this is going to yield us with, so n divided by 2 to the power n, which, and then multiply by the Riemann-Zeta n plus 1, which is exactly what we want to, find the value of. So of course I have x, so 1/2 and then to the power n, so that's the right here. But then I have 1/2 to the power -1. So what I can do is actually just put that on the other side. So that actually yields us with 1/2. So equals 1/2 multiplied by the derivative of the digamma at 1 minus x, or rather 1 minus 1/2 in other words. So that means just 1/2 over here. Okay, so that leaves the question of what value is this supposed to equal to. So now there's some recurrence relation we want to use for the digamma function, which is written as 1 minus x, and then next subtract the digamma of x, as we know that it's written as the form of pi times cotangent of pi times x. So why don't I actually now take the derivative of this entire recurrence relation over here. So now that leaves us with negative the digamma, so the derivative of 1 minus x, and then minus the digamma, so the derivative of that, of x. Then that means we have to take the, what is it? This is the cotangent, so its derivative is going to be cosecant square. And then don't forget to take the derivative inside. So that's going to be a minus, so minus, the derivative of cotangent is negative cosecant square. So that means minus pi square, and then cosecant square at pi times x. And then now let's actually just get rid of the, what is it, the negative symbol over here. So I'll just divide a -1 to everything. So that means now I have, this is the digamma prime of 1 minus x, and then plus digamma prime of x is just equal to pi square, and then cosecant square of pi times x. Now let's actually plug x equals 1/2 to this entire thing. And so what we have is that this is going to be a 1/2 and a 1/2. So we have double, so this is going to be 2 times the digamma prime of 1/2. And then over here, if I plug in 1/2 there, so that means this is actually just going to yield us, so let's see, that's actually just going to equal to just 1. So that means this is just going to be pi square. And so we just divide the 2 to both sides. So we have that digamma prime at 1/2 is going to equal to just pi squared divided by 2. And so with this, we can now just plug this back in over here. So let me actually denote that the value we solve for is that this is actually equal to pi squared divided by 2. And so therefore, that means this is actually just going to equal pi squared divided by 4, which this is our final answer to our Riemann-Zeta function of the infinite sum that we actually want to find its nice value for / closed form. Really, it's a value, but we really were just trying to find its closed form specifically for our little result to utilize everything that we just did here just now. So there you have it. But yeah, that's pretty cool if you ask me.